Dear student, today we are going to do the analysis of a convergent-divergent nozzle. We state that with the following condition, that consider air flowing at a high speed through a convergent-divergent nozzle having a circle cross-sectional area A that it varies with the axial distance from the throw. So starting with the Ansys workbench, and drag a fluid flow Fluent, and first change the properties of the analysis type from 3D to 2D. Then open a geometry in a space claim by double clicking or by clicking right click and select a space claim. It will take some time to open a space claim. So in space claim, first you have to do some settings. So click on files, click on space claim options, and change the units from millimeter to meters, and also change the grid from 0.01 to 0.1 meter, and click OK. So the changing the grid size, that is because the axial distance of the convergent-divergent nozzle is from minus 0.5 to 0.5, that is approximately 1 meter of the axial distance. So for that distance we need a grid that we can snip at 0.1 meter at each stage. So after that we have to activate the equation option from here. Sketching, click on sketch new plane and click here on the extreme right side, so that the sketching plane is basically a XY plane, and click on plane view, and the plane view will be at the front. So after that click on equation and choose custom, and in custom tab write a starting interval that is minus 0.5 and ending interval 0.5. so if the line is small and you can't see it here, then simply change the scale from 1 to 100, or if it is too small then you can type up to a 1000 scale. So as you can see that we have a line appear here. So from the problem statement, as we can see that the area of the equation is 0.1 plus x square. So we can extract the radius of this convergent-divergent nozzle from this equation, that the A is equal to pi by 4 v square, or basically the diameter is equal to 2 times radius. So we can find the value of r and write that formula in this y equation. So simply t represent here as a axial displacement. Instead of x we have t here, so t times t basically would be the x square plus 0.1 from the equation. So we have to divide it by pi, that is 3.146, and we have to take the square root sqrt. So we have to add another bracket. So as you can see that we have a curve here. So after the curve has been generated, simply click on complete button and the curve will appear here. So after completing this curve, you have to press escape to exit from this command. So after that you have to click on the line button, and because the auto snapping is on, so we have 0.33 meter distance, then we have this length which is 1 meter, and we have to snip here. So the initial axis symmetry and of the nozzle has been generated. So press escape and escape twice to exit the command. So after that we have to create it into surface, as we have concept from the surface in the design modeler. But in space claim this option is here by clicking the mode, and this 2D sketch has been converted into a surface. After generating this geometry, close the space claim by clicking the exit space claim. So now we have to go into the mesh. Before going to mesh, we have to save the project by double clicking. So for the mesh, we have to right click on insert and click on face meshing. So select the geometry and click apply. Then we have to insert the sizing and simply select the element geometry and define the element size of 0.125 meter. So make sure the units are in meter, or if it is in millimeter, then define the element size accordingly. So simply right click on mesh and generate mesh. So after generating the mesh, we have to define the name selection. So select the edge from the above and click left click on this edge and right click then, and create a name selection, that is the pressure inlet. Then simply create a pressure outlet here. Then we have our axis here. And then we have a wall here. After creating the name selection and checking all these name selection, that we have 4 name selection here: wall, axis, pressure outlet and pressure inlet. Simply close the meshing and right click on setup and update the setup. After updating, double click on the setup and start the setup module. Double click, check the double precision, and you can go with the serial option or parallel option with the number of processor. So let's say that I have 6 cores. So you can check your cores by clicking Ctrl Shift and Escape button and click on this icon to check the number of cores for your system. So I will be assigning a 6 core, or you can go with the serial button option. So first thing is to change this type of the solver, that is the density based solver. Then you have to check the axis symmetry, because we are going to solve this nozzle as a axis symmetry, and this distance will be considered as r in cylindrical coordinate, and this will be the axial distance. So the equation that will be used will be of cylindrical version of the equations. So in model tab, we are going to on the energy equation and right click on discuss model and change it into inviscid. So after that we have to change the material. In the material tab, in the fluid, double click on air and change this density as an ideal gas. We will be using a ideal gas for this analysis. So click change / create button. After that we have to check the boundary condition, that all the boundary condition that we have named in the meshing is the correct. So the axis is assigned as a type axis, that is the correct. Then we have pressure inlet, then this type is defined as a pressure inlet. Then we have pressure outlet that we have already assigned. So we have wall and the type is wall. So now we have to define some inlet condition. So in a problem that we have been given that the stagnation pressure at the inlet is basically 10, 13, 25 Pascal. So we have to define this by clicking pressure inlet and define the total gauge pressure 10, 13 to 5. And we have supersonic initial gauge pressure, we are taking it randomly, so it will adjust accordingly if the pressure, if the Mach number is basically less than 1, that is the subsonic region, that it will be automatically adjust this initial gauge pressure. So if it is already a supersonic at the start, then it will remain constant. So click OK and change the operating condition from 10, 13, 25 to 0. After that, in the problem statement we have been given that the static pressure at the exit is 3738.9 Pascal. So on a pressure outlet we have to change this pressure to a value 3738.9, and the temperature condition is basically a 300 Kelvin operating condition, that is at the inlet. So it is already basically total temperature is 300 Kelvin. So similarly here is also a total temperature of 300 Kelvin, that is a requirement. So after that we have to check the reference value, that is we have to compute it from the pressure inlet condition. So after that, from the method, make sure that the type of the gradient is least square cell based and the flow is second order upwind. After that we have to change the residual value. Initially it is 10 power minus 3, but we have to change it into minus 6. So for the continuity equation, for the energy equation, for the velocity equations, all the residual value change it to up to 10 power minus 6. So after that we have to click the initialization button, and we are going towards the standard initialization from the pressure inlet. After that simply click on run calculation and give the number of iteration to 150. Simply click on calculate. So simply click on initialize button and then the run calculation button and give a number of iteration to 150. So solution is converge at 300. So highlight run calculation and click data file quantities, click static pressure, total pressure, Mach number and total temperature from here. So we can plot the contours here, or we can plot it at CFD post. So first we will plot contours here. So let's say that we are contours, double click on the contour. Let's say that we have if we need a velocity contour with respect to the Mach number, then click on the field, save and display, and the Mach contour will be shown here. So as you can see that up to the left side of the part is basically the subsonic region, then we have a sonic region, and then we have a supersonic up to a Mach number of 2.97 or Mach number up to around about 3. So similarly we can plot our pressure contour here by simply clicking the pressure and the static pressure, save and display. So we can basically create the velocity pressure contour here. So similarly we can create the vector plot by simply selecting the velocity colored by velocity and selecting the Mach number here. So save and display, and the vector contour will be displayed here. So for the plots we have to go to XY plot here, double click here. So we will be generating basically the velocity, and this is the Mach number at the axis and the wall, and click save and plot, and we can plot the graph of the Mach number from this perspective. As you can see that we have two plots here, one is for the axis and the red one is for the wall. So that is the basically on the x-axis we have axial distance that is varies from minus 0.5 to 0.5. So as you can see that up to this region at the middle part that Mach number is less than 1, and after the throat we are going to get a Mach number that is the supersonic region up to 2.9 at the wall here. So similarly we can draw these plots in the CFD post. We are going to close this Fluent, and we are going to open the CFD post from the project tab, that is from the result. So this is the basically CFD post. You can get the front view from the z-axis. So as per this surface here, as this periodic one shadow is basically the back surface, and periodic one is basically the front face of this, and that is being revolved at some small angle because this is the axis symmetry problem. So simply check off this icon and simply click the Z button to show the front view of this 2D geometry. So first we have to create two locations. One is the axis and the second one is basically this wall location. So simply click on location and click line and give it axis location name. Simply click OK, and from domain we are going to select this all domain, and the first one is minus 0.5 up to 0.5. So simply click apply. So this line is appeared or highlighted on this frame. Similarly we are want to create the second location that is along this curve. So we are going to use the polyline and that is basically wall location. Click OK, and from method we are going to select the boundary intersection, and from the boundary line we are going to pick the periodic one, and for the intersect with the wall. So click apply, and the wall location will be selected along this line. Now we are going to create the plot against this. by simply clicking chart, and that is our, let's say, Mach number chart. Click OK. So in the series title we are going to create this plot on the first series, that is for the axis plot, and we are going to select the axis location here. On the x-axis we are going to select the distance x, and on the y-axis we are going to select the Mach number. So simply click apply. So Mach number plot will be displayed here, that is from minus 0.5 to positive 0.5, and it will go up towards the 2.5 Mach number. Similarly, for the Mach number along the wall, we are going again towards the data series, and we'll be clicking a new file, and we'll give it to the wall plot, and it is location against a wall location. So simply go into x-axis, that will be remain same, and along the y-axis it will be remain same. Click apply, and it will give you a Mach number along the wall location, that is around 2.9 Mach number. So for the plot for the Mach number contours, so first we have to change this 2D view axis meter views into whole plane by simply clicking on default legend view 1, default transform, and uncheck this instancing info from domain, and apply the reflection along a z-x plane, and click apply. And after that we have to go into contour, and let's say we have velocity, let's say we have Mach contour. So click on axis, then we'll select the Mach number, click apply. So for the click on 3D viewer, as you can see that the Mach number contour will be plotted here. So you can check the for the legend, you can change this from the vertical to the horizontal by simply double clicking on the legend view 1 and click horizontal, click apply. Then this legend will be converted into a Mach number, and the legend will be in horizontal position. So similarly we can plot the contour for the pressure by simply clicking on variable as a pressure, or you can check as a total pressure. So the pressure contour will be plotted here. So that's it guys.